Hi everyone, welcome to our second lecture related to neural encoding. We're going to describe how action potentials work and how to simulate neural spike trains. Suppose that we have a neuron here. We're going to see that this is the outside of the cell and this will be the inside of the cell. At the end we will have a cell membrane. An action potential is a concentration gradient, which is the difference in ion concentrations between the inside of the neuron and outside of the neuron, called extracellular fluid. Neurons have a negative concentration, remember this, negative concentration gradient most of the time, meaning there are more positively charged ions outside the cell than inside the cell. So look at this, positive and negative. We're going to see this later. This regular state of a negative concentration gradient is called resting membrane potential. During the resting membrane potential, there are more sodium ions outside this cell, and we have more potassium ions inside of the cell. The cell, however, maintains a negative concentration gradient, let's say between -40 to -90 millivolts. The cell wants to maintain a negative resting membrane potential, always. So it has voltage-gated sodium channels, which consist of two gates. This will be the M gate and the H gate, while the potassium channel only has one, gate N. So this will be the gate N. So this is made of potassium, and this will be for sodium. Gate M is called the activation gate, is normally closed and opens when the cell starts to get more positive. The gate H, the activation gate, is normally open and swings shut when the cell gets too positive. And gate N is normally closed, but slowly opens when the cell is depolarized, very positive. Voltage-gated sodium channels exist in one of the three states. First state is called deactivated, which is closed. At rest, channels are deactivated, the M gate is closed and does not let sodium ions through. We have another stage which is called activated, open, when a current passes through and changes the voltage difference across a membrane. This channel will activate and the M gate will open. And the third one is called inactivated or closed. As a neuron depolarizes, the H gate swings shut and blocks sodium ions from entering the cell. So there are three main events that take place during an action potential. Let's see how the membrane potential works. First of all, a trigger event that depolarizes the cell body. The signal comes from other cells connecting to the neuron, and it causes positively charged ions to flow into the cell body. Neurotransmitters are released by cells near the dendrites, often as the end result of their own action potential. These incoming ions bring the membrane potential closer to zero, which is known as depolarization. Depolarization makes the cell less polar, so the membrane potential gets smaller as ions quickly begins to equalize the concentration gradients. The neuron actually swings past equilibrium and becomes more positively charged as the action potential passes through. Repolarization brings the cell back to resting potential. So the inactivation gates of the sodium channels close, stopping the inward rush of positive ions. At the same time, the potassium channels open. There is much potassium inside the cell than out. This means the cell loses positively charged ions and returns back toward its resting state. And finally, we have hyperpolarization. Hyperpolarization makes the cell more negative than its typical resting membrane potential. As the action potential passes through, Potassium channels stay open a little bit longer and continue to let positive ions exist in the neuron. This means that the cell temporarily hyperpolarizes or gets even more negative than its resting state. Potassium channels close, the sodium-potassium pump works to reestablish this resting state.